So here, the last video discussed arc length in rectangular coordinates, but we can also go ahead and talk about finding arc length in parameterized units. So remember, these are where x and y are both dependent variables of a third independent variable t, which graphically doesn't show up on the xy plane, uh, but is our deep independent variable. So the idea of this is very similar to when we were working rectangular coordinates. If you remember, when working with just x and y, where x was independent and y was dependent. The arc length was the integral from a to b of the square root of 1 plus the derivative squared. Well, with a parameterized curve, because x and y are both dependent variables, we're going to be doing an integral from t1 to t2 of the derivative of x with respect to time squared, or square root of derivative of x with respect to time squared plus derivative of y with respect to time squared. Which, if we actually divide this whole integral by dx dt squared, gives us the arc length equation that we used with rectangular coordinates. Now, the key with this is we want to make sure that we're only going around once. And with this especially, we really do try to take advantage of the symmetry that shows up a lot in parametric curves. So if I look here at this example of x is cosine cubed, y is sine cubed from 0 to 2 pi, if I just do a quick check of the path here, if t is 0, we're starting at the point 1, 0, so this is when t was 0, and then when t is pi over 2, I'm at 0, 1, and we're moving this way. Well, if I can find the arc length from the point we started to when t is pi over 2, I just need to multiply by 4 to get my arc length to go all the way around, because I would be here at pi, here at 3 pi over 2, and back at the beginning at 2 pi. So rather than trying to go 0 to 2 pi all in one go, let's just find the arc length from 0 to pi over 2 and multiply that by 4. So to do this, I need dx dt and I need dy dt. So I have to take advantage of the chain rule with these. So dx dt is going to be 3 cosine squared times negative sine. Dy dt is 3 sine squared times cosine. So now that I have those, I am going to want to square each of those. So I get, for dx dt squared, 9 cosine to the 4th sine squared. Dy dt squared is 9 cosine squared sine to the 4th. And then I can go ahead and plug these into my integral for arc length for parametric. Now in this case, I'm going to have 4 of these, because this is just going to find from 0 to pi over 2. And we already decided it is symmetric. I would need 4 of these to go all the way around 2 pi. Of the square root of dx dt squared plus dy dt squared. Now, just like when we worked with rectangular coordinates, a lot of times if we're forced to do this algebraically, because I know you can type this into a calculator and get a numerical estimate that's pretty accurate, but a lot of times if we're doing this without the calculator, we can take advantage of simplification with algebra. So I noticed that I can pull out a 9 cosine squared sine squared, which is a perfect square. The square root of 9 is 3. Square root of cosine squared is cosine. Square root of sine squared is sine. And so I have a 3 cosine sine that's been pulled out, and inside the radical is still a cosine squared and sine squared. Now, one thing to take into account is when I do pull out my perfect squareds, technically I should be saying it's the absolute value of these, but from 0 to pi over 2, cosine and sine are positive anyways, so I can ignore the absolute value signs on those. But then I notice the square root of cosine squared plus sine squared. Well, we know from the Pythagorean identity for trig, cosine squared plus sine squared is 1. And the square root of 1 is 1. So I now have, if I move the 3 as a constant multiple out, 12 times the integral from 0 to pi over 2 of cosine t sine t. And to evaluate this integral, I can do substitution, where in my case I decided to say that u is equal to sine. So du dt is cosine, dt is 1 over cosine dt. The cosine of t will cancel out, and I will have 12 times the integral of u. Now remember, if I'm doing a substitution and it's a definite integral, I need to change my bounds from x's into u's as well. So my bounds are now 0 to 1. Oops, sorry. And now if I evaluate this integral, I've got the integral, I've got 6 times u squared from 0 to 1, which ends up giving me 6. And here is my arc length.